can move to there.
Okay, good morning, everybody, for the last day of OpenStack Summit. My name is Erez Cohen. I'm with Mellanox, with me on stage, Jacob with CSIRO, and Moshe with Mellanox as well. And we will be speaking about running high-performance workload around OpenStack. So the call name is Ironing the Cloud is basically because we're going to talk quite a lot about Ironic. For those of you that attended our lightning talk yesterday, which kind of gave a quick overview of what we're going to talk today, we are looking on high-performance computing workloads. And as you know, high-performance computing workloads are very performance-centric. They are typically the standard legacy high-performance computing workloads running in a very homogeneous type of clouds where everything is designed for performance. The hardware is the latest. InfiniBand as an interconnect for the low latency, GPUs for extreme compute, FPGAs as they're coming more and more. Basically, performance in that world is the most important criteria because they're running very large-scale workloads. Enterprise data center, however, are changing over the past few years. Modern data centers are all about programmability, right? We're looking at software defined. We want to provision everything in software, be it the compute, the storage, the network. Actually, the data center is a service providing self-services to the end users to consume the resources by themselves and by that reduce the CapEx and OpEx of the environment. It is all about elasticity and flexibility. It is all about virtualization and containerization of the application. And it is all about multi-tenancy, the ability to use one infrastructure for many different types of users and many types of workloads. So the modern data center is evolving, and the HPC community is looking to be able to utilize the same capability because the HPC workloads are changing. HPC workloads are moving from legacy workloads that were mostly around synthesis and other scientific work to more advanced workloads like machine learning and a lot of data, so all the big data and storage. Starting to get very close to what modern data centers are doing. And the HPC community is looking to be able to utilize the same technique that modern data centers are doing in HPC cloud. If you look at the HPC community, the discussion points in this community lately is all about those things. How do I run machine learning in the cloud, in the HPC workloads? How do I run containerization of application? On the right-hand side, you can see just brief part of the agenda of the last Lugano HPC Swiss conference. And more than half of the discussion points are around cloudification of the HPC workload. So definitely there's a very strong trend in research institute to move to cloud. The challenges is that with the transition to a more programmable software-defined infrastructure, there's a toll, there is a performance cost that you have to pay. The more programmable, the less performance are you. And that's true both for the computational part, but also for the networking and the storage part. Some of those elements are being addressed already with techniques like SRIOV and other things, but it is not completely the same performance as a bare metal server. In addition, in the high-performance computing, because of the velocity of new technology, it is relatively easy to plug and add new hardware capabilities, while in the cloud infrastructure, adding new capabilities like FPGA is very difficult. For those of you that are familiar with the work that in order to add GPUs to be provisioned by OpenStack or FPGA, it's not so straightforward. It is relatively very complex, and there's a lot of work every time something new is coming up. And the question is, how do we get all those good stuff in the cloud environment without paying the penalty? And our approach, at least in this talk, is to use Ironic. So we're looking at Ironic as an element to enable us to drive bare metal performance in a orchestrated software-defined environment. Ironic, for those of you that are not familiar with, is an OpenStack project that is all around bare metal provisioning, was designed initially for the deployment of OpenStack and provisioning the bare metal, but lately a lot of enhancements were done to allow multi-tenancy in Ironic and other things. The nice thing with Ironic is that it is provisioning bare metal servers. So any hardware that is there, like GPUs, FPGA, what have you, is just there. You don't need to do other stuff. You can just use it without adding more automation. The only thing that's really missing to make it really a nice story is support for InfiniBand, which is a very critical element in the high-performance workload. And this is most of the talk that we'll have today. Let me give you just for those of you that are not aware, a brief overview of InfiniBand. InfiniBand is an open standard for networking. It was designed back in 2000. Aim was to redesign the 7 layers of networking altogether, from physical all the way to application. It's very high bandwidth, low latency environment that is heavily used in HPC workloads, MPI, machine learning, and other things. InfiniBand is, as I said, very comprehensive. The specification is about 1,500 pages, 2 volumes, so very interesting material to read when you can't sleep at night. But just to give you just the basic elements that we will need for this talk, it is similar in a way to Ethernet. It has addressing in Ethernet. We're used to IP and MAC. In InfiniBand, they are called GUID and LID. They're not exactly the same, but not very much different. VLANs in InfiniBand will be partition keys. Those are having more or less the same capabilities. The software interface is not socket, but it is verbs, which allows us to run RDMA. And it is an SDN-based solution from scratch. So the SDN, the most common SDN is Subnet Manager, SM, and it's responsible to basically provision the cloud, assign addresses, and basically manage the entire cloud in an SDN fashion. And with that, I will move to Moshe.
Yeah, OK. So before we talk with Ironic with InfiniBand, let me just do a little recap of the Ironic services. So Ironic has the Ironic API, which is an admin RESTful API for managing the bare metals. We have the Ironic Conductor, which is doing the actual interaction with the bare metal, either with power management tools like IPMI or with the Ironic Python agent. The Ironic Python agent is a RESTful service that runs in the RAM disk, allows us to control the bare metal, discover its properties, or actually to start doing the deployment. And we have the Ironic Inspector, which gets these properties and add them to the Ironic node. So what is, I will give a little bit overview of the Ironic multi-tenancy. It was done in the Okata release, I think, if I remember correctly. So basically, multi-tenancy means that you can spawn bare metals on different networks in OpenStack. Usually they're using VLAN isolations, so they will be isolated. In Ironic, we also have the provision network. This is a network that Ironic is using to doing the deployment of the images. And once this phase is done, then the machine gets rebooted and gets plugged to the tenant network. So this is the basic flow of the Ironic multi-tenancy. After Nova Scheduler select the bare metals, there is the Nova Compute that runs the Ironic virt drivers. Then there is a REST API call to Ironic to do the attach VIF. This moves to RPC calls from the Ironic API to the Ironic Conductor. And then the Ironic Conductor interacts with the neutron server, create a port on the provision network, interact with the bare metal, power it on, triggering all the Pixie boot and deploying of the user image. Oops. Yeah, sorry about that. Then the conductor will delete the neutron port on the provision network, create a neutron port on the tenant network, reboot the bare metal, and then we have bare metal on the tenant network. So before I go with bare metal with ironic bare metal with InfiniBand multi-tenancy, let's look at the differences between Ethernet and InfiniBand. So in Ethernet, we have 6 bytes MAC. In InfiniBand, we have the GUID, which is 8 bytes. VLAN, in Ethernet, we have a VLAN. In InfiniBand, we have a partition key. The size are, the VLAN numbers and the PK numbers are different. We have more PKs than VLANs. But currently, in the OpenStack implementation, we map it to 1-to-1, so we still have the 4K number. DTP over InfiniBand, DTP over InfiniBand, we have DTP over Ethernet, and DTP over InfiniBand, we are using IP over IB to make this works. And on InfiniBand, we have to do the mapping between the bare metal and the IP address. We can use either a MAC or a client ID. And in InfiniBand, because the GUID is it's 8 bytes, we must use the client ID to map it to the correct IP address. Another difference we have is the DTP server. So the DTP server, when it answers for the request, sends usually a unicast request in Ethernet. InfiniBand, because we don't have ARP layer, so we need to do like broadcast the messages. And then the client knows that this is the one for him according to the transaction ID. Both protocol supports PXE and iPXE booting. The iPXE in InfiniBand is using IP over IB. So ironic multi-tenancy, so this is work we started doing. It's available from the Pike release. Currently, it supports Mellanox interconnects, requires Mellanox FlexBoot, and for doing the full multi-tenancy, Mellanox Neo, UFM, and OpenSM to give the full solutions. You can see later that this can be extended to other vendors as well. Okay, so what are the changes we did on the Upstream community? First, we changed the ironic Python agent. This is a proprietary change for Mellanox. The reason for that is we need to generate a client ID. There's no standard on how to generate it. So it's basically vendor proprietary. And also the translation from GUID to MAC, because we still kept the ironic port MAC address. This is also something that is not standard, a vendor proprietary. To use that, we use the ironic Python agent hardware management framework to control it. Basically, what it does, detect the Mellanox's IB NIC, and then he knows that he can, and if it's an InfiniBand NIC, he knows how to generate the client ID and how to translate the GUID to the MAC address. Also, when you do create the image, you need to have IP over IB model for this to work. And like I said, this is currently support on the Mellanox NICs, but because this is like a flexible framework, so other vendors that have InfiniBand solutions can also add it to the ironic agent, and it should work. So from here, this is all a common InfiniBand for all the vendors. So the work we did with the ironic inspector. So basically, when the ironic inspector queries the ironic Panther agent, he gets like all the bare metal properties. So in this case, because we need the client ID, we had to add a little change to the inspector to when he gets the client ID to push it to the ironic port. Here I have an example. How can you show? never mind. So in the extra port, you can see that we have the client ID, and this is how we know that this is an InfiniBand port. Changes we did on the ironic project, most of them related to the ironic conductor. One thing is the PXE and iPXE support. There is a little bit difference when you do the PXE boot. There is like this file that you generate according to the MAC, and there is also the field of the hardware info. So Ethernet and InfiniBand are a little bit different values. And the second thing that we changed was adding the client ID, because DTP cannot work in InfiniBand if you don't provide the client ID. So once the neutron port created, then we know we have a client ID field in the ironic port. Then we add it to the neutron port. So we will have a mapping between the bare metal and the IP address that we want to get. So this both down on the provision network and on the tenant network. If you want to create an InfiniBand port by yourself, you can do it. This is the OpenStack command to do it. You need to add the extra client ID, but you need to know how to calculate the client ID for the vendor and how to do the translation from GUI to MAC. This is not related to ironic, but still we had to do some changes to make this work. Usually disk image builder, we're using this project to create the deployment image and the ironic spectre image. So there is there a Mellanox element that loads the Mellanox drivers. We added the module to allow it to load the IP over IB. We also had a problem with the timeouts. So there's a big difference between how much time an InfiniBand and Ethernet interface it takes time to get up. So we had to fix and provide a timeout configuration for that. If you want to create inspector image or deploy image for that, this is an example how you can do it. You need the Mellanox element, ironic agent. You can provide any OS you want. And if you want to do it deploy bare metal, you can choose this element as well. On the neutron side, this is work we did on Kilo. Not for this use case, but for a use case we have neutron as InfiniBand SRV support. So what we did there, we allowed the neutron agent to allow to be configurable to send broadcast replies. And also we added a change to the agent to use a client ID. So there is a bit different on how you specify all the other DHCP options and the client ID, because it's doing the one-to-one mapping. Here in the example, you can see the DHCP broadcast reply flag that you can set to make it work with InfiniBand. So this was all good for actually also for flat network to make it work. To do a full solution with the multi-tenancy, the missing part is the partition keys, the P keys. And for that, Mellanox has a solution, including the Mellanox SDN mechanism driver that's currently supporting both Ethernet and InfiniBand fabrics. Just send REST API indication to NEO. NEO is a cloud networking orchestration and management software. Again, we are using it both to Ethernet and InfiniBand. In the InfiniBand use case, it's talked to the UFM, which is our InfiniBand fabric manager, and that allows to open the partition key. Basically, just configuring the partition key file in the OpenSM. So how this flows looks like. We have the neutron ML2. It gets the, once I want to create the port either on the provisioning or on the tenant networks, and neutron get the indication. We have our ML2 plugin that sends the REST API to NEO. Then NEO can indicate either if it's Ethernet or InfiniBand fabric. we are focusing on the InfiniBand. So once it's in InfiniBand, it sends an indication for the UFM to open the P key on the partition key. And then we have the full multi-tenancy solution. Thank you.
Thank you, Moshe. I would like to share with you a case study done from a customer's perspective. I'll tell you a bit about how we're planning to deploy Ironic with software-defined InfiniBand at the CSIRO. First, a couple of words on the organization, because not all of you might be familiar with it. CSIRO, or the Commonwealth Scientific and Industrial Research Organization, is Australia's national science agency. We are a big user of scientific computing. We've got about 2 petaflops of compute and 50 petabytes of storage in-house. We are a Mellanox Center of Excellence, hence we're working very closely with Erez and Moshe. We're looking mostly at high-performance cloud computing and artificial intelligence at this stage, but we might expand this to other areas. We are based in Canberra. However, we have a strong presence all around Australia, and also we have offices overseas, North America, South America, Asia, and expanding. We also have a global network of partners. So why are we looking towards private cloud? Traditionally, we've been a big user of batch queue shared HPC systems, and that's been working for us very well. However, in the last few years, we see increasing demand from users for either custom dedicated high-performance computing systems that are configured in a significantly different way than our shared systems. And we also see growing interest in cloud. So we have a significant EC2 user base with a fair bit of growth there. So we're thinking about possibly insourcing some of those workloads. And also, we are investing in cybersecurity research quite heavily. It's a topic of interest of the Australian government. Hence, this brings new set of challenges to scientific computing and cloud computing in particular, because obviously we need stronger security, because we do trust the users, but we do not necessarily trust the malware they're analyzing on the systems. And isolation is an important thing in this particular context. And the last main driver of looking into private cloud systems is we see a fair bit of fluctuation in the demand and utilization of our systems. So if they're partitioned as separate entities, it's rather difficult to smooth this out. However, if we look at converting systems into applications, ideally cloud-native applications, we can use cloud-specific scaling techniques to smooth out those spikes in demand and make user experience better. So for those reasons, we decided to embark on a journey towards significant investment in private cloud. And just having a quick look at the tools we traditionally use inside of computing. As I mentioned, we're a big HPC user, and HPC provides us top performance, and our users love it, and they'll never, ever give it up, ever. It's not an option. On the other hand, we have a variety of cloud-based, cloud-specific tools that have much more flexibility than what we normally use in high-performance computing. And if we can come up with a way to find a solution, if we can find a solution that could provide both the raw performance of the HPC and the flexibility of cloud, this is something that would really help us. That's something that would have a lot of value for the organization. So with this in mind, the question becomes, how do we have the cake and eat the cake? And that's a birthday cake that our friend Dan made for myself and my wife a few weeks ago, and we had a big problem. It's so pretty, you can't really eat that. So we ended up slicing it in half, freezing half, eating half. Now, the good news for you guys is we don't have to do that when it comes to high-performance cloud. There is a solution that can deliver us the top performance that we're used to from batch queue systems, and also the flexibility that we're seeking at specific to the cloud world. So we believe that by going with Ironic and SD and InfiniBand, we can have all of those features that we need. So flexibility of API-driven access to a pool of high-performance resources, and the performance that our users are used to and are not going to give up. And we believe that using this platform, we can build next-generation solution that will take full advantage of the high-performance NVMe-based file system we're building as well. So with this file system, we are aiming for hundreds of gigabytes a second and millions of IOPS. So obviously, we wouldn't be able to take full advantage of this by utilizing a traditional virtualized cloud with TCP-based storage. The benefits do not end here. As Erez has mentioned, there are lots of things that need to happen to make HPC work in cloud, lots of optimizations we used to apply. Good news is we don't have to spend time doing any of this if we take a bare metal approach, because all the optimizations that we've got on the metal will just transparently move over, and any new device that we might want to have will just work, assuming it's supported on Linux. There is no extra onboarding required anymore, and that used to be a case and used to be a pain point with more traditional cloud approach. And last but not least, KVM adds to latency, and the MPI doesn't necessarily like that. So I think that the bare metal approach will make our MPI users very happy. So this is the improvement in performance that we expect from moving from a legacy KVM-driven system with TCP and FS storage and moving to a bare metal cloud with high bandwidth InfiniBand interconnect, EDR at this stage, and HDR in the near future. Now I would like to give you a quick demo of what the end-to-end provisioning looks like. Moshe has described all the details and technicalities, and what I will do is I'll play a video that captures the flow. I used the video because we just don't have time to go through a full provisioning process on the hardware. The blades just take too long to boot. So I wrote a simple Ansible playbook. For those of you who use Ansible, this will all be very simple. For those of you who are new to this, Ansible has very powerful OpenStack modules, and those can be used to talk to OpenStack APIs and instantiate infrastructure in a very simple and very powerful way. So I'm using the network modules and the OS server module to instantiate the instances. All right, let's go. I'll move to the corner here so that I can use the pointer. So in this part of the screen, you can see the Ansible playbook running. And as it starts creating neutron objects, you will see the flow on the SDN controller here. And we'll be zooming in to see what exactly is it doing. And here will be the OpenStack view with instances, ironic, and neutron. So you can see that the network has been created on the SDN. And the neutron agent has been added to this network. So you can see that the GUID of the agent, see the host name here, is now in partition key 4, which is our tenant network. Now, the playbook has concluded, so in a few seconds you will see more action here as the temporary entries are created for the blades, which are being put in the provisioning network. And as this is happening, you can see the Nova instances showing up here, the instances being allocated to blades showing here, and then there is some neutron information here, which is less relevant because we're just looking at it from the tenant perspective, so we can't see everything. See, if you follow the flow here, you will see all the relevant GUIDs and pickies. Now, this just captures the PXE boot process over InfiniBand. For those of you who are familiar with Ironic, it's pretty similar to the standard one. We're using FlexBoot on a Mellanox NIC. This is something that's different. This stage indicates that the HCA has been able to make contact with the subnet manager. And now we're just going with DHCP, so I'll jump this a little bit. In the interest of time. So we can see that the PXE boot process has started, just pulling the RAM disk and the kernel. Again, jumping ahead. Now, this is one of the parts that Moshe has described, so I wanted to touch on it just a little bit more. Those blades have a lot of connectivity. They have 4 10 gig ports and 4 InfiniBand ports, hence this is a bit longer than what you normally see. But the important part is we had to increase the timeout on the DHCP to match the specifics of working with InfiniBand, because things take a bit longer. Good things take time. So you can see this happening here. And we need to wait for the other interfaces to time out, so I just cut that step, and we're moving forward. Now we're going back to the more holistic view of the cluster. What you will see now is as the IPA image is spooling up, you will see state transition in Ironic. Maybe I'll indicate it on the big screen. So this is starting right now, and that means that the image is being written onto the local storage of the blades. Now, the really interesting part is as soon as this is completed, you will see transitions on the SDN as well. So as Moshe mentioned, there is a nominated provisioning network that we use to write the image to the local storage of the blades. And then, as soon as we're done with that, Neutron is transparently moving the blades to the tenant network that's been requested on creation. So I had that in the Ansible call over there. So let's see where we're at. The blade is deploying. I'll move this forward a bit to save time. OK, we're done with the deployment, and in a few seconds, we'll see changes happening on the SDN controller. There we go. And I'll zoom in to explain the details of this in a second. So the provisioning network partition key is being removed for the GUID of the blade. And now we're moving it to partition key 4, which is our dynamically created tenant network. And the PKey is already here because we created the network already, so that's just doing nothing. And the very same set of actions will now happen for the other blade, but in interest of time, I'll just jump ahead a little. Yeah, so we can see that the same has now happened for the blade 8. Yeah, this is just to prove that the image has been written onto the local storage correctly. So you can see the tenant requested image spooling up on the hardware now with full IB support. And this is to illustrate some of the actions that Moshe has described. I'm just going through the list of blades in Ironic, as well as the bare metal ports. And I wanted to highlight the mapping between them, as well as the extra information that's gathered by the IPA, because that's what's been going through the SDN controller throughout the whole presentation. So you can see the GUIDs here, and those final bits might seem now familiar, now that we've been through the demo. So this is where Neutron is getting the information from, and this is then relayed onto the Neo SDN, and then onto the OpenSM that changes the GUID to partition key mappings dynamically on demand. And this concludes the not the presentation, just the demo. Let's go back to the presentation screen. So just to sum it up from our perspective, the real value of Ironic with SDN IB is that it combines the raw performance of HPC, which we need, with the flexibility of cloud that we would like to have. And we believe this will be a game changer in how we work, because this allows us to apply DevOps and infrastructure as code methodology to high-performance computing, which gives us that flexibility and ability to make things dynamic that we've been lacking, and that HPC users worldwide are seeking, as Erez has said, based on his conference feedback. And we believe that this will pave the way for the next generation of lightweight, highly efficient scientific computing platforms, and that's a great asset to us. So we're very excited to be on this journey, and we'll be pushing forward to transition this POC into production in the coming months. OK, just a few words on some of the challenges we've been facing. There has been a lot of work happening upstream around adding flexibility to Neutron network configurations. This configuration you've seen is just a single rail configuration. However, given how we run at the CSIRO, we need multiple fabrics to connect to multiple storage backends and so on. So that's something that's been lacking, and in Queen's release, we can do all of that. So we'll be adding this very shortly. Something that we're routinely hitting while running high-performance computing and high-performance storage is PCIe bottlenecks. So we're looking forward to transitioning to PCI 4. Because while building this high-bandwidth NVMe system I touched on earlier, this is the main problem. We have to work around the limitations of PCIe, which we shouldn't be doing. So we hope as the new platforms become available, we'll not have that problem. We'll be able to accelerate even more. And as Moshe has mentioned, we have the ability of scaling way beyond what's possible with Ethernet and VLANs if you're using VLAN drivers. However, we need to work on the HCA firmware to fully enable that. And with this, I would like to conclude the presentation and open the floor to questions. Thank you.
So I might have missed that part, but were you forced to spawn these bare metal nodes serially? Like I was wondering in your demo, you were just showing, saying now the next node is going to start doing the same thing. Is the work being done serially, or you can, is there any limitations for deploying everything at once in hundreds and hundreds of, potential nodes?
No, there isn't, and this is what controls it. So the fact that they booted in a serial-like fashion is just a coincidence. Normally, they just fire up straight away. So it's not ironic, it's just how the Dell hardware works. So if we put 100 here, it would most likely work. We only have 30 in the environment right now, but I don't see a scalability problem at that number. Thank you.
You mentioned multi-tenancy before, and usually multi-tenancy is based on network isolation with VLANs, dynamic allocation of VLANs in the switch ports. Is that what you do with the ML2 driver that you also mentioned?
It is very similar. I would like maybe Moshe or Erez to answer this.
Can you hear me okay? Yeah, so it is similar. It's not VLAN because InfiniBand is not using VLAN, it uses partition keys, which is something similar, more enhanced. But basically, we're configuring partition keys. Unlike Ethernet, where you need to go and configure the switch port individually, in InfiniBand, because it's an SDN concept, you can configure the SDN controller or request the SDN controller, and it will configure the entire fabric for you. So all the flow that Moshe mentioned about connecting Neutron to the SDN layer is what enables that, basically.
So from my perspective, we're not touching the switches. We're just talking directly to the heart of the fabric, which is the OpenSM.
Is the Ethernet over IP over IB driver back on the roadmap now for OFED?
Yeah, so that's a good question. So Moshe mentioned that we're using IP over IB and Ethernet IP over IB. There are slight differences between them, but in general, IP over IB is an enhancement of IP over IB, which is not yet part of the upstream work of Linux. We're in the process of working with the community to make it upstream so that it will be part of any operating system. Right now, it is coming as part of Mellanox drivers, Mellanox OFED. In the last release, it was not updated. From the next release and on, it is back on track. And hopefully, someday, it will be just upstream.
I have a question. So what about scaling this to really high-scale multi-tenant network? Do you use VXLAN at all?
So we can use VXLAN. Right now, as I think both of us here explained, the deployments are relatively small. Partition keys can be scaled for very large. So it's unlike VLAN, which is kind of across the network. Partition keys can be mixed and matched so that even if we have 15 bits filled, which is quite large space, we can even multiply that more. So we can scale to very, very large in theory. In practice, we have not implemented that. There's some challenges around providing the DHCP services, and they need to all go to the same VLAN or partition key, which there's some work that we need to be done. But it can be done. It will be done, I guess, if there will be a need from the community.
Just to add to Erez's response, I think even as it stands, the solution would be sufficient for us to deploy the next generation supercomputer in this fashion. We probably just have enough peaking bandwidth to do that, given our usage patterns, where workloads are rather large. But if we had a lot of small workloads, that can become a bottleneck, and then we're hoping to work together with Mellanox to address that if we hit it. But it's pretty good as it stands. Could be better, but to us, I think it's sufficient at this stage.
Okay, I think we're done. Thank you very much, everybody.